Okay, so in the past we used graphical means in order to add vectors together. And the way we'll be doing it moving forward is actually using what we call Cartesian vectors. Cartesian vectors are basically breaking the vector up into x and y directions. Remember, we resolved into just general vectors or general directions last time. Now we're going to break into an x and a y direction. So we have an x direction like so in the horizontal and a y in the vertical, and they're 90 degrees apart, which makes our math much easier using trigonometry, which is the study of right triangles, which is essentially what we have here. Okay. Now, in breaking those up, we need to define what we call a unit vector. And a unit vector is basically this I vector and j vector, which is a vector that has a magnitude of 1, okay, in a specific direction. Okay, so this unit vector basically designates the directions of the x and y axis. So if I multiply any scalar times the I vector, I'm saying that that scalar, that magnitude is in the x direction. If I multiply it times the j vector, I'm saying it's times in the y direction. And because the magnitude is 1, I'm not changing the value of the magnitude. Okay, I'm just giving it a direction. So we could write a force vector like I have here as the force in the x direction times the I unit vector plus the force in the y direction times the j unit vector. So again, I have this magnitude fx in the I direction and this magnitude in the y direction, and I multiply that times the j vector. So this is how I would represent a vector in Cartesian form, using the x component times I plus the y component times j. Now, oftentimes we're given this force vector and I want to resolve it into the x and y directions. I essentially want to find the x component and the y component. Now, what I have here is a right triangle, right? Because x and y are perpendicular, we can use trigonometry to figure this out. Okay, so if I'm trying to find the x component, right, that's adjacent to this angle theta that I have here. Okay, so hopefully you remember from trigonometry that the cosine of an angle is the adjacent side of the triangle over the hypotenuse. So the cosine of theta here is f sub x divided by the magnitude of f. Okay, same thing for the y component. Okay, remember this magnitude and this magnitude are identical. So the sine is the opposite over the hypotenuse. So I have fy over here divided by the magnitude of f. Okay, now through algebraic manipulation, I can actually figure out that the x component is simply the magnitude of f times the cosine of theta, and the y component is the magnitude of f times the sine of theta. And we will do this hundreds of times during the class. So you're really going to want to figure out how to do that, and we'll do it in class and figure it out from there. But that's how we represent a vector in Cartesian form. We break it into x and y components, or horizontal and vertical components, using I and j vectors and using trigonometry. Now, once we do that, we can talk about vector addition. And really, this kind of picture I have up here is why we would do it this way, because we can easily add 3 or more vectors together using Cartesian vectors. Using the graphical approach, I can really only do 2 vectors at a time, and this way it works much more efficiently when I have several vectors. Okay, so the first step is to break each of these vectors, f1, f2, and f3, into its Cartesian form, form. Basically, find the x and y component of 1, the x and y component of 2, and the x and y component of 3, recognizing that, for example, f2x here has a negative sign because it's acting to the left in the negative x direction. Positive x is to the right, positive y is up. Likewise, my f3y is negative because it's acting down, positive y is up. This component is acting down, so I have this negative sign here. So the first step in adding forces is to break them up into their x and y components. Okay, and we do that just like we did on the previous slide using trigonometry. Once I do that, I simply add up each component. So I take my x components, my f1, my f2, and my f3, add them up, and my fy, f1y, f2y, and f3y, add those up. Okay, and so I take this one, I subtract off this one, and then add f3x. Likewise, f1y plus f2y minus f3y. And what I wind up with is the resultant force in the x direction and the resultant force in the y direction, given like this. And I can write that vector like this, where I have the resultant force equal to the x component that I summed up times I plus the y component that I summed up here times j. Now, if I wanted to find the magnitude of, say, this resultant vector, or really any vector, I can just take and use Pythagorean theorem, knowing that this side plus this side equals the hypotenuse squared, right? This side squared plus this side squared equals the hypotenuse squared. So I take the square root of that, and I can get the magnitude, basically the length of this vector. If I want to find that angle, I simply use an inverse tangent, right? Here's my y component, here's my x component. Divide those, take an inverse tangent. So that's how we're going to add vectors moving forward, right? Break each force up into x and y components, sum up your x's, sum up your y's, and solve for your resultant force, finding a magnitude and angle if that's necessary.